Yo, good evening. Please alert our people to join in. Right. Good evening, everyone. Please respond with a thumbs up if you can hear me clearly. Thank you for the brief action by that. So, welcome to another session of Dcit 207 of the makeup class. In tonight's session, we will be covering some of the labs that have been assigned to us. All this in an effort to better our understanding of the course. If you have any question pertaining to something we've previously discussed, feel free to raise your hand and then ask before I proceed. All right, that's clear. All right, so we stop there. Before we tackle the labs, I believe you've gone through them, right? If you have gone through the labs or whatsoever, then I think this will be a plus for you. Plus, yesterday I also dropped a task on the platform, and then if you had tackled it, then maybe you may have gained some good understanding of the concepts of it by now. So I want you to hold on right now. I'm going to open the task from yesterday, and then we look at what happens in it if you tackle this. That is, how many of you tackled this? Please raise hands if you tackled the task, or if you did not get time to that school. Okay, then it means nobody tackled the task. That's Sana Mutia. All right, then let's study. Okay, so this is the lab that we have been assigned by our lecturer, and it has quite a few phases to it. So let's look at them one by one. So there is the lab one, and then the lab one relates the von Neumann. Yes, Mr. Joshua.
Mr. Harrison, please, can you change the theme of your listing?
The theme of this one
Yeah, the interface. It's dark.
is that, yeah, I can see that. Why does it? Is it distractive? I'm sorry, I was thinking.
Yes, something like that.
Okay. Okay, so since I'm using the web interface and changing it will mean I will have to go into my Microsoft account and update it there. So give me
Okay,
about
sure,
2 or 5
sure.
minutes to just yeah. Yes, very true. Oh. Shut the fuck up. Am I already yes, no? Yeah, hello, Charlie. I do the cloud is you, so I don't know if you can manage, but you see, it's not like your normal interface. So I'm trying to find it and not locating it. Looks like I'll have to sign. I've tried going on their sites. I go to the settings, but I do not see the theme among the settings there. Even if I click settings right here, I do not really see it among the options. So, Mr. Joshua, is it that bad?
It's okay, sir.
Yeah, sure. Okay. Else that would mean I'll just have to use a different software, but it will take a while. But right. So as I was saying, we are going to be discussing the details of our lab. The lab one. The lab one is a relation between the von Neumann model and then the Littleman computer basics. We already know the basics of Littleman computer. So we are just going to see how the Littleman computer runs programs in relation to how a von Neumann architecture works. So we have to identify the components of a von Neumann machine and then the stored program concepts. Execute a first Littleman computer program step by step to fetch, observe, fetch, decode, and execute. And then we have to refer to the Stollings Manual, chapter 1.1 to 1.4. I have them in summary, so we'll display that later. All right. So everyone, open your Littleman simulator. Use the very same one that I forwarded to you yesterday. It has quite the friendly interface and it still provides all the necessary details. If you have this particular what do we call it, opened. If you have this the lab opened, you can copy the program details here. If you don't, I'm going to put them on our page right now. So um you just paste it in there without the addresses, the lines at the addresses at the back to indicate their individual the order that they should run. Because the interface you are going to use provides all that automatically. So you can copy it and then paste it over there. All right. And also for those who want the link, I think this is the link here. Okay, so let me just copy the link from my page and forward it to you. So I've put the link as well as the codes on the instructions on the platform, and so you can follow that way. All right, so let's not waste much time. Let's just get right into it. My keyboard has lost functionality on some keys due to some current fluctuations that I've been exposed to. So bear with me. All right, so this is the interface we are using today. Can you all see it clearly? If you can, just react with a simple thumbs up. I assume no one can see it then. Mr. Venix, Antivida, Mr. Joshua, Mr. Asari, Prince, Abwaje, Prince, every single one.
Yeah, I
Okay.
can see.
Hey, and I'm on female. Wow.
I react. You said thumbs up. I did that.
Oh, sorry. I didn't see anything. Sorry. All right. Let me fetch the instructions from this side. So we have inputs store at 90, load 90. Let's go back to it. So please, if you have your Littleman computer program open, run it now and launch it. I would like someone else to share so that I'll use their screen to explain. I think whenever we do that, it's more interactive and then it's easier for the individual who is doing it to follow and also understand. So today everybody is going to share their screen, okay? So if you are with your PC, that's it. But if you are not, that's cool. So first off, this is it. Let's see the details of the program so that we will know what to end of the lab, so that we'll know what to take notes of as we are working. So it says run in single step mode and record PC, instruction register, accumulator per step. Now you see, if we run in single step mode, what will happen is that each single instruction will have its separate micro sequence for fetching, its separate micro sequence for decoding, and its separate micro sequence for execution. Each single program. That's going to give us a lot of steps. So instead of running them in steps, we are not going to run them fully. However, we are going to rather run them in cycle. Okay. So we run them one cycle and then we record the data per the table that I forwarded on the platform yesterday. So if you drew a table like that one, you'll be using it. If you are not having that table, by the way, I think I can also forward it to you. I can forward that to on the platform. However, today we'll be using mine, and then after the what do we call it, I will forward that on the platform. So we are going to run the programs in cycles. It says we have to run in single step mode and record the program counter, instruction register, accumulator per step. Then we are going to have to, so these are some of the things we can divide. It says completed table of the program counter, instruction register, accumulator per step, and also a brief explanation of the stored program execution. It also goes further to say in the lab 2 that we have to trace each micro operation from load, add, and store, and map them to the sequence they follow from the program counter, memory address register, memory buffer register, instruction register for each single one. So this is where we are going to have to break it down little by little. So for the first one in lab 1, we'll run by cycles, and we are only going to run by steps inside the lab 2. And then the last one says we have to relate Littleman computer cycle to the instruction cycle states installed in chapter 3. I have that summarized somewhere. I'll pull it up later. All right. So let's first do the lab 1. So these are the instructions for the lab 1. Input, store, 90, blah, blah, all the way to this. Before we run it, by now, I believe you are all familiar with how the Littleman computer operates. So I want you to share with me what you think will happen at each step of running. If I tell the computer inputs, blah, blah, what do you think are going to be the changes that will occur in my program counter, my memory address register, etc., etc.? Do you think there will be any changes, or do you think there is nothing going to happen because we said inputs, but we've not really inputted anything? See, the way nobody has raised their hand, it means nobody knows. If I'm going to point somebody, yeah, that's how we write. All right, let me look through. Let me see. Hey, Boham Richard Nana Kwame. Boss, I don't think I've ever heard you speak on a meeting. Or how are you doing? Mr. Richard Nana Kwame, how are you doing? Hey, Richard Wadana. Okay.
I'm good. I'm good.
Okay. Well, I don't think I've ever heard you speak in a session, so
Well,
would you
I can
like
listen.
to would you like to share, or you will wait a little?
I'll wait a little.
Okay. If nobody goes, I'll come back to you. So hold as you are waiting, please be thinking of an answer. Okay. All right.
Okay.
Bless Tobo or Tobo. Yeah, Tobo. What about you? I want to know what you think will happen should we run the first cycle on inputs. What happens to the program counter? What happens to the memory address register? Is there any changes that we should expect to see at any place? And then outside them, yes, please.
Yeah, hello, good evening.
Evening.
My laptop is at fault, so I'm now trying to. Right now, I'm enjoying using the phone.
All right, that's cool. That's cool. But don't worry, I'm not asking you to run. I'm just saying maybe you know. So to everyone, whether if you have a phone, no, it's cool, okay. But I'm asking, do you know what will happen to the program counter or the memory address register or the memory buffer register when we hit run the first cycle on the input instruction? Yo, Joel, do you want to share?
Okay.
Okay, yeah.
I just joined.
All right, Charlie. I heard your mic was unmuted. That's why I was thinking you wanted to share. Okay, Auntie Vida, let's go. Vida, you may speak here.
Yeah, so the program counter holds the memory address of the next instruction to be executed.
Good.
It will hold the address of the
That's right. So it's going to hold the address of the next
the
instruction.
memory address of the next instruction to be executed.
Oh, okay, that's
Right.
cool. Everyone, clap for Vida with a reaction nicely. She has said exactly what will happen. So she says that the program counter will hold the address of the next instruction to be executed, and then she couldn't have put it any better. That's exactly what happens. So now let's run it, and then we see where there will be changes. I want you to follow carefully with your eyes, and do not get distracted, okay? Okay, so let's see. Okay, so now what have we noticed here? We are trying to fill in our table. There is a table we are filling in. So what have you noticed? When we hit run cycle, one cycle, what happened here? Let's make this as interactive as possible, okay? It will help you recall the things we've learned. We've been studying these things for a while, but some of us do not remember anything. It's not because we are slow or anything. It's just because of the fact that we do not constantly cooperate. Yes, Auntie Vida, what did you notice?
All right, so the opcode at first it was 0, right? At the
Good.
control unit, at
Yes.
first it was 0 and it changes to 9.
9. Okay.
Yeah.
Good. All right. So Vida has noticed that the opcode has changed from 0 to 9. That's one. What else? Aside that, is there any other thing you saw? Did you see anything concerning how the program was flowing? Yes, Mr. Joshua.
Okay, so I noticed that the program counter changed from 00 to 01.
Okay, that's another increment too. So that's a different change as well. So one person has noticed change in opcode, one person has noticed a change in the program counter. But then one thing that we should also take a good look at is the program counter fed data to the memory address register. So you realize that the value here traveled down from the program counter to the memory address. That means the program counter was telling the memory address register that use the memory address I have given you, which was 00 at the time, which corresponds to the instruction here, 0 input. Use that, visit memory address 00 here. You see that? And then it says, go and retrieve the data that is over there. So it retrieved the data there, and then it carried it through the data bus, gave it to the memory buffer register. So then input has an opcode of 901. So then if it takes this code, it is basically taking the instruction as inputs. It holds that value inside the memory data register, since that's what we're executing. Then it gives that value, which is the instruction, the same instruction, to the current instruction register that you see up here. You see that? All this while, you realize that as it was running, the control bus give an instruction. There was a small time where values move from the control bus into the memory and stopped there. This means the control bus is coordinating the flow of the program. And after this happens, from 901, the inputs has now been recognized as the current instruction, and then it has been entered into the control unit. So this is what the control unit is going to execute, 901, which translates to the word inputs. So now you can see that the input box is now open for us to enter data. Let's enter data. Let's use our lucky number. What's our lucky number even? Let's just use 2. Okay, everybody likes 2. And hit enter. Once we do that, I want you to follow carefully. And this time, so you tell me what has happened. All right. So when we entered this, where was there a change? Where was there a change?
The accumulator.
The accumulator. Excellent, the accumulator. So then we are going to, Mr. Emmanuel, Mr. Emmanuel, your hand was up. Or that was it, the accumulator.
Yeah, I wanted to answer, but
All right.
I've answered already.
All right. So we are going to use this very information here to complete our little man computer table, and we are going to do it step by step so that we don't get confused. So we are using the cycles. When we run cycle 1, the program counter increased from 00 to 01. Then the instruction register received an instruction. What was the instruction it received? It received inputs, INP, right? So the instruction it received at the time was INP, and you can even attach the opcode if you want, which was 901. And then the accumulator received nothing before we entered our inputs 00. And then the explanation at this point will mean that the program counter, yes, antidivider.
Yeah, hello. Please,
Yeah.
the little man computer laboratory table, no.
Yeah.
Is it on Sakai? Because I've looked for it. I'm not seeing it on Sakai.
Oh no. This is a self-made table. So we are just, this is how according to what the lab said, this is how the table should be given. So that's what this yes, please. You don't worry, I'll share this one later, and then you can also fill it with your own data and from observations. Yes.
Okay, thank you.
Yeah, so then the explanation on this side will be that the program counter prompted the memory to fetch data, or in other words, to go to the memory address indicated, which was 00. And then after it did that, the program counter, the memory address register went into 00, took the instruction in the memory address register, and then brought it out. Okay, so we can say PC let's use ADDR for address. All right, let's proceed. So now we entered our input for the second step, 01. And then when we did that, what did you notice? You said the program counter this time will now increase to 02. And then when it does, the instruction register is still holding the instruction inputs because no new instruction has been entered yet. And then the accumulator received the inputs that we gave it. So let's see what the accumulator received. So then the accumulator received the inputs we gave it, which was 002. All the while, you can see that you can see it here, 002. You can see PC stays 01, and you can see that the current instruction register, or the IR, still holds the instruction, which is input on 901. So then the accumulator is the only one that changes in this instance. So it changes to 02, like that. And then what this means is that the value that we entered as an input has now been loaded into the accumulator. So let's not bother writing all those instructions little by little, but for explanation's sake, we'll be mentioning them as we go. Now we run another cycle again. Good. So then when we run the next instruction, store 90, just tell the memory or tell the computer, the PC, that the value that we have entered as input, store it in the memory address 90. So then, even though we are not yet addressing the memory address register and all that, you can see here that the memory address register is now holding the address of the current, what do we call it, memory space to be used. And that is what, 90. And then the current instruction register is using 390, which means to store a value. So then it is saying store. It's telling them to store, and store where? Store in this address, which is 90. So then it's the memory data register is now reading the data that is stored in address 90, which still happens to be 2. And the accumulator is still holding that value. Remember, the accumulator holds a value that is being that operations are being conducted on. So then the accumulator is holding right that. So we can go back and then update our table. Some of the values will stay the same, but what changes here currently is the current instruction register. On the third run, it changes to 390. Accumulator remains 2. So then at step 3, so I'll leave the other cells as they are, and then they will be filled later. But then the accumulator stays the same. The instruction register now changes to LDA, which we know to be what? According to the code, we saw 390. So instruction register is either 390 or LDA, one of them. All right, let's proceed. I meant store, not load. So that was STA, right? Right. Let's proceed. Now we run again, one more cycle. Good. Now, is there anything that you think we have omitted in our table before we proceed? Some values are updating, but we are leaving them out. So now, can you tell what has changed that we have not taken into account? When we're at step 1, the program counter will be at 1, holding the address of the next instruction to be executed. Upon running it the second time, the program counter is going to update to 2, holding that's the address of the next instruction. This means when we are at step 3, which means we are going to the next line, which is line 3. Program counter needs to be on 3. Remember, these steps are just how many times we have run, by the way. So we run it first time, then program counter updated all the way to that. All right. So then when we just did the loading, more values have been updated again. What you can see as a difference currently is this, that the current instruction register has updated again because of the load instruction. So the current instruction register holds the exact instruction that you are executing in the moment. That's why it's called the current instruction register. So that has updated to 590, which corresponds to the load. So it says load the value stored in data address 90. So what did we store in data address 90? It was the value 2, right? So then the memory data register will now have the value, the current data that we are talking about, which is 2, is being held in the memory data register. So then let's go and update our table accordingly. So we will say the accumulator, it still holds the value because we have not done any operation on it yet, so it still holds it. However, on the next level, this updates to load 590, and then the accumulator still holds the data value, which is 02. So the instruction register is the one that is currently changing, and it is only changing because there are different instructions to be executed. So it's always holding the current instruction that we are working on or to be executed, or at least holding the opcode for that instruction. All right. Then we move on to the next one. The next one is the outs. Let's see that. Good. So then look at what has happened here. The accumulator and then a few other things have stayed the same. But the current instruction register, the memory data register, the memory address register, they have changed. The program counter has also changed. So there's a lot of updating to do. So the program counter is now holding the current address of the next instruction, that is 4, telling the program that once we are done with this, we are moving to the 4th line. Then, if you read on your memory address register, it is holding the current address where we are running an instruction. The current address that we are running an instruction at is address 3 here. And that's where the address holds the instruction, which is halt. So if you come to address 3 over here, and you see address 3 over here, you notice the way it is holding the halt instruction, which is 902 here. Is here. Sorry, it's holding the output instruction, which is 902 on this side. And then if we move on to the current instruction register, it is also holding that very same instruction because it's telling the computer what it's supposed to execute. Then if we come into the control unit is now executing that instruction. And then after that instruction is executed, the accumulator pushes the data that was being held outside into the output space here. So let's keep that in mind. And then we can go and update our table accordingly. Okay, right. So then when we move on to the last step, it was the out instruction, right? So the instruction is what you will see. Let's check what the other parameters that were updated were. Right. So then the out instruction 902, the accumulator still held the 2 because no operation was done on it. On this side, the program counter updated to memory address 4. And then here will be for the last one. We overlooked something. No, program counter starts at 00, 01, 02, 03, 04. All right. So then if we run the program one last time in a single cycle, that will be the halt. And then you see halts in memory address, the opcode is 000. It has been carried. It is now being transported to the data bus, goes to the memory data register. That holds it, sends it to the instruction register. That sends it all the way to the control unit, and the control unit executes it, and then the program successfully halts. So now, this one here that we have done, we have traced the instructions all the way from the program counter, and then we follow the sequence all the way to the end. But we have not traced them on the micro level. Remember that each single instruction, when we did input here, it has its own separate fetch, decode, and execute cycle. And that's the micro instruction and the micro sequence that the second lab was talking about. And if we take store, it also does the same thing. And then load also has the same thing. Each one has its separate one. Right. In that process, we are going to have to explicitly state what happens. So you will mention that the program counter holds a value. And then you can use an arrow to indicate that it prompts the memory address register. You see that? It prompts the memory address register to do something. So then it tells the memory address register to visit this memory address or says, this is the memory address we are using. Then the memory address register then goes to that address, and then the memory data register reads from that address and contains the data. And after the data comes to the memory data register, if it's an instruction, the current instruction register holds that instruction. And that instruction is then used to execute the program by the control units. And then the one that transports this information are the buses. So the address bus carries information to the address. Data bus carries data information to the memory data register. The accumulator, on the other hand, does the operations and then displays as and when needed. Before we proceed, if you have any good questions, this is your time to ask. So in today's one, we are just dealing with the labs. And when we are done later, we are also going to further our knowledge on the little man computer and then run a few programs on it with some simple instructions. Okay, so since there are no further questions, I'll assume that we can all say we have seen what the lab one is about, and then we can clear it with confidence. Mr. Joshua,
I don't know. Can you hear me?
yeah, please, I can hear you.
It's like my Arithmetic computer interface is a little bit different from the one I'm using.
I cannot hear you clearly. Say, come again.
I say it's like, okay, I'll send you a message privately because I'm in a car.
Okay, wait. You said your little man computer interface is a little more complicated.
The one we're using, the one we just used right now.
And the one you are using is complicated than the one we are using, right?
Yes.
Okay, so you know something, I have put a link to the one we use right now on our IT Makeup Masters platform. So it's one of the last messages. So you can just tap it and then it will redirect you to the page if that's okay.
All right, sure, thank you.
Yeah. All right. Okay. So then let's listen closely. In the next one, we are going to personally map the operations of the little man computer. Personally, we are going to follow with our eyes, and then you will clearly state, here run away, no. The program counter carried this to that, this to that, this to that, this to that. And after doing all that, it gives us this output of that. So this one says the lab 2. We are using looking at the instruction fetch and decode execute cycle mapping. We are to trace each micro operation. So we are tracing the micro operations. Mr. Joshua, please, you still have something to say? Your hand is still up, or is from the first time?
Oh, sorry, from the first time, I'm sorry.
All right, good man. So then we have to trace each micro operation for every single step. We follow it from the program counter to the memory address register to the memory buffer register, which is the same as the MDR, to the instruction register. And then when we are done with that, we are going to relate the LMC cycle to the instruction cycle states in the stallings. That's the fetch, decode, and execute. So this time, this is the program that we are going to use for that. So let's copy the instructions. So if you are with your PC, copy the instructions so that you can also follow and then give us the inferences. And this time, I'm going to allow you all to follow with your eyes and tell us what exactly is happening. So if you are going to copy your codes and paste them here, in case you copy and they are not working, come to this button right here where it says stop. Yes, Mr. Joseph Pa Kujo.
I beg, there's no link in the group. What kind of link are you talking about?
I say, what kind of link are you talking about? Okay, I'm coming in. Mr. Joshua Anand, boss, can you go to the platform and then reply to the link so that they can tell which link we are using?
Okay, sir, sure.
Yes, please. Let me put these instructions in the platform as well. Okay, so I will do that while I'm at it. Unless, of course, the person is not on the platform, then that's totally understandable. So let me drop it in the chat as well, just in case. So, Mr. Pa, the one who just spoke, I'm putting it in the chat for you, so you can access it from the chat as well. Okay. Let me also add the instructions for you. All right. So, Mr. Pa, please check the chat, okay? I have dropped the link as well as the instructions, so you may use that. Okay, so to the rest and to all in attendance, let's proceed. So here's our instruction. All right. So here are the instructions we have. We have load 10. So it says load the data stored in address 10, add 11, store in 12, halt the program. Oh, okay. It looks like I cleared a little too much. I'm going to update the data I put out there. So since it says we should load address 10, then we can only assume that address 10 was already assigned a value. So it means that 3 here was referring to 10. Yeah. And then this one to 11, that's 4. And then 12, that's 0. Yeah, so I want you to follow me with your eyes to this region right here, and let's explain some of these instructions to you. We are already familiar with what the load instruction does. The load instruction retrieves or reads data from a particular memory place and transports it somewhere else. And then we have the add, which of course adds. And we have the STA, whose job is to store the data in a particular address. And we have halt, whose job is to stop the program from running endlessly. Then we have these DATS instructions. Basically, they are called data instructions, and they are used to tell the computer or the little man computer that this particular region is holding a particular data value. So do not use it for any other running. We are aware that in a von Neumann architecture, data and instructions are all stored inside the very same space. Therefore, if you do not assign memory locations on a lower level, if you do not assign them to particular what we call it as particular storage, the computer is going to end up using them to store your instructions, and then you're going to have your program failing. So this one here, you see the value at the back of it is the memory location, and then the value in front of it is always the data stored in that location. Is that clear? So 10, that's 3, means we are storing the data value, which is 3, inside the memory location 10. So then, if we come to memory location 10 on this side, once the program runs, this side here should now be having the value 3 inside it. 11.4 means on at storage space 11, hold data value 4. And then when you see that 0 here, it basically tells the computer that this side is for instruction, is for data, so do not touch it. So when you say 12, that's 0. This means you're not specifying what exactly the data value stored at 12 is. However, you are telling the computer that at 12, I am storing a data value, so do not use it to store instructions. I hope that makes sense. Does that make any sense?
Please, can you go back again a little?
Oh, okay. Thank you for the honesty. Right. As I was saying.
Yes, please, back.
Okay. So it makes sense. All right. So let's start with the first line again. Some of the instructions here we are familiar with. LDA is the load address instruction. It is used to load the data stored in a particular address. This one here. We all know that, right? If you know it, that's a good thing because we've studied it already. And then we have add. The add instruction is used to combine values. And since we are dealing with a little man computer, we can only combine 2 at a time. So the add instruction is used to combine values. And then we have the store instruction, which is used to save data to a particular memory location. And then we have the halt instruction, which is used to stop the program from running endlessly. Then we have these DAT instructions you are seeing here, DAT, DAT, DAT. These are basically instructions that are used to tell the computer how it should store data and where exactly it should store it. For example, if I tell the computer 10, that's 3, I am basically you see at the back here is a memory address. Is that clear? So 10 here is a memory address. In other words, a memory location. The 3 you see in front of it, or the values you see in front of it, are data values to be held in the memory locations. Mr. Joshua, does that make it clearer to you? Joshua,
Yes, I'm clear, sir.
all right. So then this means that if I go to address 10, I am storing the value 3 inside it. So 10.3 means in address 10, store data value 3. That means 11.4 is going to mean in address 11, store data value 4. And then 12.0, when the that value is 0, it basically tells the computer that this side is designated to data. So telling the computer that do not store instructions here. It says assigned to data. So do not store instructions here. So basically, when we run the program, all these things you are seeing here will be telling the program how exactly is to manipulate data. Okay, that's basically it. And there are several ways you can use this. We'll look at some. So this means if I want to tell the computer that a memory location, like maybe a memory location like 50, is holding a particular data value, like let's say 7, I will just say 50.7, implying that if you go to memory location 50, store the data value 7 inside and do not use it for anything else aside that. This is similar to what we know concerning variables. If you make a variable a constant, so for example, if you are writing a code and then you make a variable a constant, say you say age is equal to 11. Whenever you call age, it is always going to display the value 11. So then we are doing something similar here. It is different from merely feeding inputs. This one here tells the computer that always at the address 11, the data value is 4. This means no matter how many times I run the program over and over again, at address 11, the data value is also going to stay 4. Okay, so they are used to assign data to particular memory addresses so that the computer doesn't use them to run other instructions. Is that clear? All right, let's continue. So now let's reset our PC, our LMC, and then, yes, Mr. Felix.
Okay, so that, please, I want to know the values assigned to these memory addresses. Are they in their nature, are they constants or they are variables?
The values assigned to these memory addresses, in their nature, are they constants or they are variables? Okay, so
Yes,
let's view them this way. A variable can be made into a constant, right? That's provided it is not going to change as the program runs all the way to the end. So if it is going to be called on and then it is supposed to maintain its value without changing, then that variable becomes a constant. What this means is that the data being held inside these regions up until they are asked to change, they are constants. It's like when you write a simple program, a program that calculates commission for somebody, and then the commission is 5%. Inside that program, 5%, you are going to store the value, the variable which was commission that you created, and then you are going to assign it to the value 5%. This will mean every single time you call on commission, 5% remains constant, irrespective of what calculation you do. So whether the person sells 1,000 CDs or 1,000,000 CDs, the constant commission will still be the rate 5%. So with that logic, we can conclude that these values will also be held as constants in this particular code's instruction. So then it means for every single execution that we do, data at 10 will stay 3. It remains that way and doesn't change. So they are being held as constants. So the data values inside these regions are being held as constants. Mr. Freeman, does that explain, does that answer your question?
Oh, okay, thank you
Yes,
very much.
please. All right. So please, let's run this quickly, and then let's see what happens to the program as we do. Remember this one, we are trying to trace each single cycle. The cycle goes like this, sorry. You should just keep track of how these things are changing. Your program counter, your memory address register, your current instruction register, sorry, your memory data register, and your accumulator register. I have already compiled a table with all these values in it. Yes, so we are just going to follow with our eyes, and then later we are going to reference that table and see how well we did. So I'll call on you one by one, and then you will be telling us exactly what happened, who carried what to who, etc., etc. I'm going to use this space right here to be, writing the answers you give. However, it's not part of the code. Yeah, that will interfere with my running. I almost forgot. You know what? Let's just go ahead and run it. So then this time we are going to do it in steps. So I'll hit one step. Watch it carefully. So when we hit the first step, what did you notice? PC carried to MAR, right? So the program counter went to the memory address register. But still observe the fact that there has been no change to the value in the memory address register. If we step it up again, the memory address register now carries the address it has been given and visits that address space, telling the computer that we are going to read data from address 00. Now that the computer knows that, the job that follows will be for the control bus to tell the computer to let the memory data register go and then retrieve data from that storage space. Let's see, that's one step. Good. So the control bus gives the instruction read. Did we notice that it gave the instruction read? We step it down again. Now the data bus carries data from the memory address to the memory data register. Are we following? Then if we step it again, the memory data register now carries that data value, which was the instruction, by the way, to the current instruction register. We step that again. So this is the micro sequence, okay? Once we step it again, that instruction is sent to the control unit to await execution. So the control unit decodes it. It decodes the instruction. We step it again. And this is all for the load command, by the way. So we are still on the LDA. So this is the micro stepping. That's what it means. So now that it has been decoded, the program counter increments to 1. So it means we have now successfully finished doing the LDA and we have decoded it. Now the program counter now holds the address of the next instruction. And then study this. LDA says, at memory here, it says 10.3. So it means if you go to address 10, store the data value 3 there. So let's keep stepping and see if that change happens eventually. So the program counter told the memory address register, that we are supposed to do something here. It says we are going, in the next line, we are going to address 01. However, currently the memory address register is overriding it. You realize that now the address the memory is holding is different from what the program counter is telling it. So can anyone tell us why exactly the memory address register is suddenly visiting line 4 when it should be on line 1 or line 2? I think it should be on line 1 even. Because the program counter says on the next instruction we should go to add 11. But the memory address register is obviously visiting line 4. Why is that? Any hands? Is there anyone who has any idea why the memory address register is currently not following what the program counter is telling it to? Well, the program counter told it to execute 00 before it pointed to 01. Yes, Mr. Joseph Parkojo.
It's because you told it to load 10.
Because we told it to load 10.
10. That's why I skipped all the way from 1, 2, and 3.
That's excellent. That's excellent. So then he has said exactly what it means. That because we have told the little man computer, or we have told the CPU to load the value stored in the memory space 10, it is now referencing this side that tells it that inside memory space 10, there is data value 3. Now, this instruction is on address line 4. You see that? It's on address line 4. So the instructions that you have given, they are also stored in memory spaces. So currently, if we go Hello, everyone. Sorry. I got disconnected. Okay, Vodafone Wahala. I'm back in the game again. Let's continue as if nothing happened. Sorry. All right. Yeah, please, you can all see my screen, right? I'm very sorry for that little mishap. So, as Mr. Yahoo, I forgot his name. What's as he? Okay, yes, as Ankwanda Joseph, powerful name. As he was saying, currently, the reason why we have skipped all the addresses and have jumped to address 4 is because address 4 holds what we want right now. Address 4 holds something that is key to loading 10. Because when we are loading from 10, we cannot load from 10 without going to the instruction that says 10 contains data value. So I'm saying that even your instructions, they are stored in the very same space that your data can be stored in. And this is the whole idea of the stored program concepts and then the von Neumann architecture. So if you do not assign spots to your data, you might end up storing it in a region where instructions will later be stored and then contradictions. So currently the program is also overlooking the program counter's direction and it has gone to memory address 4. to go and then retrieve the data value there so that it can go and store that according to the memory data register. It can carry that information and later load the data value, which is 3. If you study 004, it is holding a value here, 3. And then that value is going to be loaded back here into address 10. So let's continue with the stepping. The control bus has communicated with the RAM to read. And the data value is carried from the RAM region, that's 3, transported to the memory data register. Now it's holding that value, 3. So we have loaded the data successfully. Then the data has now been successfully loaded into the accumulator. So take note of what is happening here. The current instruction register is still holding the load instruction, which is 504. So that is holding that. So now we are in the accumulator. We have loaded the value into the accumulator. Next instruction says that add 11. So you can see the current instruction we are standing on is here, is the load. Next instruction says add 11. Add 11 means we are going to have to go to address 11. The values you see in front of the normal instruction addresses is only for the data instructions that the values at the back are the memory addresses, and these ones are data values. Keep that in mind. So then when we see stored in memory address 11, so if we run this code right, then the computer should jump again. The little computer or the control unit's CPU, should jump once again to all this side, number 5. It should dump every single code here, come to memory address 5, retrieve the data stored there, bring it to the accumulator, to the memory data register, combine it with the value in the accumulator, and then hold the value that the accumulator has. So I want us to add an output instructions, but we have already come quite far in it, so I don't want to stop and start. So when we are done, we'll add an output instruction so that it displays our outputs. Let's keep the game going. So we step again. The program counter now tells the memory address register that move on to address 1. That's this one here. So now the program counter says move on to address 1. Address 1 says add 11. Then the memory address register is going to tell the PC which address we are visiting, address 1. Now the control bus tells the machine to read. The memory data register now reads the data value that was stored in address 1. That's an instruction. The instruction is add 11. That instruction is carried to the instruction register. So now the instruction being executed is the add instruction 105. Instruction is then carried all the way to the control unit to be decoded and understood by the computer. Now that the computer understands what it is, now it can execute. So then it says add. So now it's executing it. It takes back to the memory address register. So then what do you notice? The memory address register is now holding the address of the instruction to be executed. And that is what? Storing data value 4 inside address 11. So it says the memory address is now 5. Step again. So now we have told the computer that the current memory we are using, that's the job of the memory address, tells the computer the current memory that we are reading or writing data from. And that's how it differs from the memory data register. One tells us where we are standing, one goes to where we are standing and takes information. The control bus now prompts the machine to read. Little man computer then reads the data from the address 5 into the memory data register or the memory buffer register using the data bus. So now it is holding the data value 4, and it's going to feed that as an to the accumulator for the combination to happen. The arithmetic logic unit now takes both values, and then what does it do? It does an operation on them, right? So when it does the operation, it is now going to store the new data value inside the accumulator. So now the accumulator holds the sum of our data values from 3 and then 4, 7. So this is what happens when we step the run. We are stepping it one by one. So action about no 1, 1, 1, 1. That's basically what we are doing. So now we have finished the program execution for the art. So you see it fetches. Let's follow what we did right now. It fetches data. After fetching the data, it now decodes the data. Decoding the data is done in the control unit. After the control unit decodes the data, it now executes. So execution means it follows through the right channels. If it is an addition, blah, 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 it prompts the accumulator to feed those values to the arithmetic logic unit to conduct mathematical or arithmetic operations on it. And after these operations are conducted, the accumulator now holds the answer to that operation. So now the program counter has been updated to 2. Telling the computer that now let's move on to STA 12. Is that clear? All right. So now, what do you think will happen when we move on to STA 12? Does anyone have any idea what happens at STA 12? Is the memory address register going to make a sudden jump again, or is it going to maintain the normal part of the program counter?
It's going to make a sudden jump.
It's going to make a sudden jump. Thank you, Boss Freeman. So then he says it's going to make a sudden jump because there is an instruction that says, or that tells us what exactly 12 is for. So then let's step this program again. So then the program counter has now fed its current data register, its current address, so the memory address register. So that the memory address tells the computer where we are reading data from. So the memory address now says we are reading from address number 2, so go to that side and retrieve information. Control bus now tells the program to read. Memory data register goes to do the reading and carries the data into itself. So then that data is an instruction. So I'm saying data instruction, sorry. So it carries the instruction into itself this time. The instruction has been fed to the memory data register. And then that's going to be carried to the current instruction register. Current instruction register is now going to carry that all the way to the control unit. So the control units will now decode it. So let's step it again. So when it decodes, you realize that after decoding, it separates it into the opcode and then the operand. Now, I want to know this. This opcode, this operand, what is the difference between the two sides? And why does the decoding matter? Is there anyone here that knows how the opcode differs from the operand and why the computer decodes it by separating the two? Hey, Obiani. Wow. There's no one amongst us who knows how the opcode differs from the operand. Are you sure? Tell me so I don't know. We'll go and sleep. Why are you amazed? Okay. Right. So then let's see what these two things is. These two things are, sorry. The opcode and then the operand are two regions of an instruction, basically. That tells the computer exactly what to do. You see, the opcode here corresponds to a particular instruction. So for example, apart from some instructions that have fixed codes, the add instruction, as you can see, it says 1, x, x, implying that 1 remains constant. That's the opcode. So then 1 corresponds to add. But the XX, that is the operand, it differs because sometimes we may be adding from a memory address. Sometimes we will be adding a raw data value. That is what XX is about. So the operand tells us what exactly we are adding. So if we are using the add instruction, are we adding 2 RAM spaces? Are we adding raw data? are we adding from a particular storage area? That's what the operand is about. So the first part you see here corresponds to an instruction like add or store. In this case, you see 3 corresponds to the store instruction. And then the operand XX, in this case, is 06. This means we are storing in a particular memory address. So let's keep that in mind. The opcode is an instruction. The operand is like a particular operation that is supposed to be done by that instruction. This means the opcode can stay the same, but for the same opcode, you can have different operands. Is that clear? It doesn't remain constant. Opcode will stay constant for a particular instruction. So the opcode talks about a particular instruction. However, the operand may differ depending on what you want that instruction to do for you. Is that clear? So can we now see the difference between the opcode and then the operand? Or are we still confused? Do you have a question on this?
Please, can you take it again?
Oh, okay. Thank you for your honesty. Right. So then we said, think of the opcode, the first value. Currently, let me see. You see the current instruction register is holding an instruction that says 306. This instruction is composed of an opcode and an operand. So then the opcode in the control units, decoding will mean we are separating the instruction into its opcode and its operand. The opcode is the instruction. Whereas you can think of the operand as what exactly the instruction should be used for. So for example, if I tell the computer add 20, add is the opcode, which corresponds to a particular value in the CPU, which is 1. And then 20 becomes the operand, which might be a memory location, might be corresponding to a particular data value stored on a certain line, or etc., etc. This means opcode will always correspond to a particular instruction, therefore it doesn't change for a particular instruction. Every add will have the opcode of 3. But sometimes, depending on what you are combining, the operand for the add is going to change. So the operand basically tells us which particular addition we are doing. The opcode tells us we are adding, yes, but the operand specifies what we are adding. Which memory location are you adding? And that's basically the difference between these two things. And that's why the decoding is important. So the computer is taking the instruction in a human form. And then now it is breaking the instruction into a way that it is more understandable to it. Not even in a human form. It's not in a human form. It is taking it from a little higher and breaking it down into a lower way that it can understand better. And then it will proceed to execute. So, boss, does that explain it better to you?
Yes, please. Thank you.
Yeah. So the opcode is the operation code, whereas the operand is either the data or the address we are using. The opcode is the operation code. And then the operand is the data or the address that we are using. The opcode tells the CPU what to do. And then the operand tells the CPU what to use. Opcode tells the CPU what you are doing, you are adding. The operand tells the CPU that, oh, you are adding from address number 5. You're adding from address number 27. Opcode tells us what to do. Operand tells us what to use. Let's not forget that. So you can view there, in an analogy form, you will say the opcode is a verb. And then the operand becomes the objects that the verb is acting on. Good. So the verb is the opcode add. And then add address 6 becomes the object. So the address 6 becomes the object or something. Okay. So then the opcode stays the same for a particular instruction, but then the operand can change. Our time is basically over, but we have learned quite a lot. But let's finish this side, and then I will show you the table of values for what we have recorded so far. So we run again. It's now, so you see, it carries the address, right? the address here, 6. That's what is being held at the operand though. So the opcode said 3, which means we are storing. And then address 6 on this side will tell the computer that we are using the instruction on line 6. So visit address number 6 and then go and proceed from that side. So then currently it is telling it an address to use. This means if it was 7, our opcode would have stayed 3, but then the operand would have changed to what? 7. So if this instruction was on line 7, our opcode would have stayed 3, but the operand would have changed to 7. So opcode will stay constant for a particular instruction. However, the operand will vary depending on the address or the data that we are dealing with. Let's not forget that, okay? Next time in the lesson, if the lecturer asks, let's wow him with these things. Let's proceed. Now, since we are storing a value, it says we have to store the value from the addition, right? We are storing it in the address number 12. So when we just hit for step, you realize that the accumulator carried the value it was holding, which is 007. Hey, James Bond. Carried that to the memory data register to be held there. So then in the memory data register now, we are holding the old value. We are storing it there inside here. So we are storing that there. The data being stored is that. So the execution has been done. So if we step it again, we read what is being stored on that side. So now it says carrying the data. So you see the memory data register can either read or write. So now we have carried the data to memory location 6. And after we carry it to memory location 6, the memory data register is later going to retrieve it again, and this time store it in memory location 12, as per the instruction of the computer. The reason why we have carried it to memory location 6 is memory location 6 is holding the instruction of the storage of the data. So it's going to temporarily hold the data until the execution of that instruction is completed. Then it will move the data, or rather copy and transfer it to where it's supposed to be. The program counter increases to 3. Here the whole no. Control bus prompts the computer to read. It carries the data value that it has read, which is 000. And we step that again. Current instruction now becomes 000. And you can see that the halt instruction is initiated with a 0. It means the opcode for halting is 0. We step that again. And it is decoded. 0 as the opcode, 00 as the operand. And then we have halting the program. So, bling to bling, we are done. The program counter now updates back to 00 again. So then, this is the micro operation sequence that the lab 2 was talking about. I hope that is clear. It looks like we finished right on time. That's why it's been 3 minutes late. It's more fun to say when the network cut and I went and I came back. I hope I have done a good job at explaining. But if my explanation didn't meet what you expected, don't worry. Maybe in our next lesson, I'll make it up to you. I'm sorry for the inconvenience and then the network breaking earlier. I want to show you the data, the table that has these detailed things. I prepared this and put it at one of these spots. It's this one. Good. So let's see. All right. So here's a table that shows all these things. I'm sorry for the dark screen you see, but it seems very clear to me. All right. So here we go. The micro operations are what you are seeing here. So it says when we step the program the first time, the program counter is at 0. Instruction register holds no instruction. The memory address register is also at 0 because the program counter tells the memory address register what to do. Visit address 0. Then the memory buffer register still holds no data currently. The accumulator also holds no data. It holds 000. But the micro operation happening is that the program counter feeds the memory address register with an address. So you see, it says PC points an arrow to the MAR. Let me expand this table so that you will see it properly. Good. So now you can see it says PC tells the MAR what to do. So this is the micro instruction for when we loaded the very first one. What was the very first one? The loading first one, it was what? Load. Good. So just the load, the first step of it. So we are currently fetching. Yeah, fetching. So then after doing that, we go to the second line. Program counter is still on 00. We have not yet moved. The instruction register still holds no instruction. We are still fetching. Memory address register is still on address 0. Then we now go to address 0 and see what it says. Address 0 tells us that we are loading 10. So inside address 0, the memory data register holds the exact 10 that was coded there, which is load 10, which means load memory address 10. The accumulator still has 00. The memory buffer register, then we see the arrows properly. Oh, there's the max. Okay, good. The memory buffer register now has the data inside it. So the memory address register tells the memory buffer register that go to this particular address and read information from there. So after it tells it that it does not hesitate, it quickly goes there and it goes to carry the data value. And after carrying the data value, the instruction register is now updated. We saw the sequence and all that's happening. So this is just the micro sequence, the micro sequence for the first instruction. But the ODH here, you can see it's quite long, right? So it's Dcit. It traces each single one. I'll forward this table to you later. You can follow it with your eyes. And the final state is what we saw. The accumulator now holds the value 7. And then the memory location 12 is also holding the value 7. So then let's see if the accumulator really holds the... Oh, I think we resetted it. Yes, but you saw it. In the end, the accumulator had the value 7. And then the memory address also was telling the RAM a bunch of things to do. So finally, the value was stored in 12. It has been a great time with you. Good evening, a good night to everyone. Have a good night's sleep. And then I hope you have a great day tomorrow. Thank you for your time. Goodbye. Sorry, if you have any questions, go ahead and ask. Yes, Mr. AK. Being the AK-47. Oh, yeah. Mr. Joseph Parkojo. Powerful name.
Bye-bye. Thank
Please
you.
bring your what's it called, your screen back.
Hey, sorry. Which of the screens do you want to see? The little man computer?
Yeah.
Yeah, okay, we are here.
Okay, so the DAT, what does it stand for?
Ah. You were not here from
I
this
want,
side.
no.
Okay, sorry. I'm just pulling your legs.
Yeah.
Don't worry, I'm just pulling your legs. DAT stands for data. So it just tells the computer that, yes, it's an instruction that tells the computer what we are using data for, where we are holding the data, which data will remain constant. So everything concerning data is on this side. So currently what you see here, you see 10, that's 3. Simply means whenever we are using the data instruction, the first value is a memory address. Unlike the other instructions where the last value is the memory address, in this one, the first value is the memory address. And then the value in front of it is a data value. You see that? So when we say 10.3, we are telling the little man computer that we are going to store data value 3 at memory address 10. So then the data instruction just tells the computer which memory slots have been specifically or explicitly, let's use critical thinking words, assigned to data values so that the computer will not end up storing instructions in them. So you realize the way when we're running our things, you see currently when we come to address 5 on our little man computer, address 5 is holding a data value 4. But we didn't state in our codes anywhere that address 5 should hold data value 4. This means the computer on its own is storing this particular instruction on line 5 inside address 5. So if you don't specify exactly where data is to be held, the computer will end up storing instructions where your data should be. And if you try retrieving data from a place where instruction is stored, your program is going to fail. So the data instruction tells the little computer that, aha, yeah, the data na share, instruction be You see that thing?
Yeah, I get you because I was confused where the 10 and is now loading from 3. You get?
Oh, okay. So, but is it cleared now? Is it cleared?
Yeah,
Is the
yeah,
confusion cleared? All right. You are the
yeah.
boss, Charlie. All right. You're the man. You're the man. Any other questions? All right. So on this note, I would like to bring our meeting to an end. Obia and Koda, and then dream good dreams. My boss will say, if you don't dream, you're a suspect because you are probably not sleeping. Everybody go and sleep and dream good dreams, and then see you tomorrow. I think our next session will be with the all great Mr. Isaac. We come and teach you some skirmishes. Later you meet Mr. Freeman, very powerful gentleman. Goodbye, everyone. Have a great night.